produce polarization. This is what we do, right? Apply an electric field and you want to find out how much is the polarization. So let's say we want to look at polarization in the I direction. So this we can say is given by polarization in a certain direction can be created by applying electric fields in every possible electric source. So if I had applied, let's say, an electric field in the jth direction, still there is going to be a polarization in the ith direction. So let me denote this by the symbol some chi ij. Is that okay? And then of course some over. This is one thing we can state, right? So this is of course the response is linear. Apply the electric field and it produced the response which is proportional. I should not actually put it that way. I will say that when you apply an electric field to an object, in general it can lead to movement of the charges, positive and negative charges, a redistribution of positive and negative charges in the medium, leading to creation of electric dipoles. How much is the electric dipole created, of course, would depend upon the strength of the electric field, but it need not be simply linear in the applied electric field. Okay? So it could be quadratic, it could be cubic. In fact, there could be responses to all orders in the electric field. This is the simplest part. So if we are looking at the linear part of the response, we write it in this way. So we can say to that point, there can be another thing like this means this is the second order response. This means the response of the system depends upon the square of the electron. If I write it like this, you can see I, J, K, L. And so on. So if you are interested in studying nonlinear medium, then you're basically going to look at either this response or this response. Usual materials, these coefficients are very small. But there are materials in which these either the second order or third order coefficients are substantially large and they are used for very many purposes. For example, let's say you want to have a way of producing photons of lower frequency than the photons that we have. Let's say we have a laser, it works at a certain frequency, let's say in the ultraviolet. And using that one, we want to produce, corresponding to every photon, let's say you want to produce 2 photons. Then that means basically you are downgrading the frequency of the system. So you start with the frequency omega, let's say you want to have 2 photons of frequency omega by 2 each. Such things are possible. And these things are actually having a lot of use when you learn non-classical aspects of quantum mechanics, something called quantum entanglement and so on. So there is now, kits are available commercially. Actually, I can make this suggestion to the teachers also. We can make some gadgets to illustrate the principles of quantum mechanics to students very easily with the laboratory experiments. Okay, very easily doable with optics. So there what you do is, you have a crystal, called BBO. I think it is called beta, no, I think barium bismuth oxide or something like that. I don't remember exactly the name of that. But it is BBO, shorthand name is BBO. You send photons of frequency omega here, lead to 2 photons of frequency omega by 2, and there will be a definite relationship between the polarizations of photons. For this crystal, I think these two will be having the perpendicular polarizations. For certain other materials, these 2 photons coming out will be having same polarizations. So you will have very controlled way of producing pairs of photons whose polarization is fixed. How does it do that? It does it because of the fact that this particular coefficient is unusually large for that material. So this simple example tells you tensor of rank 2, tensor of rank 3, tensor of rank 4, etc. One simple physical law. Similarly, you can have the magnetic analog. So this is an example where it is the same type. Now we can also have piezoelectricity. Apply an electric field, it produces a stress. That will give you the simplest one in that case would be having third order. Okay. So let's say you apply a stress and you want to produce an electric. So stress means basically you have to have two components. You apply a stress here, and let me use some other symbol here. So let's say the electric field produced is apply a stress, it leads to production of an electric. Stress has to be specified with two indices. Okay? And of course there should be one index corresponding to the response direction here. So ij here. You get a third rank tensor. Now this can be further generalized. This is linearly applied stress here. Now we can think of quadratic response in the stress here. So that will be a fifth order tensor and so on. So this way when you want to look at physical properties of systems, responsive systems in general I would say. Okay. The responses can be linear and then non-linear also. All those contexts will be encounter tensors. But all these components here, no? These components will depend upon what was the coordinate system that we have chosen. I will repeatedly state this. If we change the coordinate system, the stress tensor will change. The response has to be still the same, obviously this has to change. So these two things together have to transform in a very, very specific manner. That means you can say each one of the components here will have to transform in a very specific manner for this physical object to be meaningful.
In this case, that sigma will transform by similar form.
Yes.
The other one will be one form.
Yeah, that's right. So you can look at that, and maybe we can have another full meeting for discussing tensors.